What if I told you that gravity, that force that holds galaxies together and keeps our feet on the ground, might just be a side effect of temperature? This is the main idea behind a fascinating concept called the thermal theory of gravity, or TTG. It's a bold, new way of looking at the universe. Instead of thinking of gravity as the bending of spacetime caused by mass, this theory suggests something else. It proposes that differences in temperature across the vast emptiness of space can create the same effects we call gravity. Imagine heat flowing from a hot place to a cold one. The TTG suggests that this flow, this thermal gradient, could be what bends the fabric of the universe itself. This idea challenges our most basic understanding of the cosmos. For over a century, Albert Einstein's general relativity has been our guide. It tells us that mass and energy warp spacetime, and this warping is what we feel as gravity. This has been proven again and again. But the thermal theory of gravity doesn't necessarily throw out Einstein's work. Instead, it adds a new layer to it. It suggests that the energy part of Einstein's equation might be more directly related to thermal energy than we ever imagined. It's like finding a new recipe for the universe, using ingredients we already had, but in a completely unexpected way. Think about the universe on a large scale. It's not all one temperature. Some spots are incredibly hot, like the hearts of stars and bustling galactic centers. Other regions are super cold, like the vast empty spaces between galaxy clusters. The thermal theory of gravity says these temperature differences create a kind of pressure. This thermal pressure in spacetime could push and pull on objects, mimicking the effects of gravity. It's a radical thought. Gravity might not be a basic force as we thought. It could be something that just pops up, born from the rules of heat and energy, the rules of thermodynamics. So where does this leave us? We're at a crossroads of cosmic understanding. On one path, we have the familiar road of general relativity, paved with the heavy ideas of mass and spacetime bending. On the new path, we have the thermal theory of gravity, lit by the glow of thermal energy and temperature differences. This new way of looking at things asks us to rethink everything we thought we knew about the force that controls the cosmic dance of planets, stars, and galaxies. It invites us on a new journey of discovery, to explore the universe through the lens of heat and its amazing unseen power. One of the biggest headaches in modern astrophysics is something we can't even see. We call it dark matter. For decades, we've seen that galaxies spin much faster than they should. Based on our understanding of gravity, the stars on the outer edges should be flying off into space. To fix this, we imagine a huge halo of invisible dark matter surrounding each galaxy, providing the extra gravitational glue needed to hold everything together. But we've never directly detected this mysterious substance. The thermal theory of gravity offers a surprising alternative. What if there's no dark matter at all? What if the extra gravity is just an illusion? This theory suggests that temperature differences within and around galaxies could perfectly explain these strange rotation curves. A galaxy isn't just a collection of stars. It's a dynamic thermal system. The center is hot and dense, while the outskirts are cooler and more spread out. According to the TTG, this natural temperature difference would create a gravitational effect that gets stronger in the outer regions. This effect would make stars orbit faster, exactly as we observe. It's a beautifully simple explanation. It replaces a mysterious invisible substance with a physical property we can actually measure: temperature. And what about dark energy? That's the other big cosmic mystery. We see that the universe's expansion isn't slowing down. It's speeding up. Something is pushing everything apart, acting like a kind of anti-gravity. Scientists have called this force dark energy, but we have no idea what it is. It's another placeholder for our ignorance. The thermal theory of gravity also steps in here. It proposes that the overall temperature gradient of the entire universe could be responsible for this cosmic acceleration. As the universe expands, it cools, but not uniformly. This cosmic-scale thermal effect could be the engine driving the accelerated expansion. So, the thermal theory of gravity comes forward as a possible solution to two of our biggest cosmic puzzles. It offers a unified explanation that doesn't require us to invent new exotic forms of matter and energy that make up 95% of the cosmos. It suggests that the answers might lie in the physics we already know, the physics of heat and energy, applied in a new and profound way. This doesn't mean dark matter and dark energy aren't real, but it gives us a compelling and testable alternative. It's a reminder that, sometimes, the most elegant solution is the one that simplifies, rather than complicates, our picture of the universe. The deep connection between gravity and thermodynamics isn't a completely new idea. Think about black holes. Stephen Hawking showed that black holes aren't truly black. They have a temperature and slowly radiate energy, a process known as Hawking radiation. This was a groundbreaking link between the laws of gravity, like black holes, and the laws of thermodynamics, heat and entropy. The thermal theory of gravity takes this connection and expands it to the entire universe. It suggests that this isn't just a special case for black holes, but a basic rule for how space-time itself behaves. It's as if the universe is one giant heat engine. From this viewpoint, gravity is deeply connected to entropy. Entropy is often described as a measure of disorder or randomness, but it's also about the natural tendency for energy to spread out, to flow from an ordered state to disorder, from hot to cold. The TTG suggests that gravity is a force that comes from this very process. As the universe grows and its entropy increases, the resulting heat changes in space-time create gravity. This is a big shift in how we think. Gravity is no longer just the quiet stage where the cosmic drama plays out. Instead, it becomes an active player, a result of the universe's unstoppable march towards heat balance. Think about the early universe. It was incredibly hot and packed together, a state of very low entropy. As it expanded and cooled, structures like stars and galaxies started to form. This process of forming structures is also a process of increasing entropy. The thermal theory of gravity would say that as these hot, organized structures formed against the cold, disordered background of space, the resulting temperature differences created the gravitational fields that hold them together. Gravity, then, is the force that helps the universe organize itself into pockets of complexity, all while following the basic rules of thermodynamics that control the flow of heat and the increase of overall disorder. This paints a beautiful and complete picture of the cosmos. The rules that govern a cooling cup of coffee on your table could be, in a deeper sense, the same rules that govern the dance of galaxies across billions of light years. It connects the very small and familiar with the very big and mysterious. It suggests that the arrow of time, which is so closely tied to the increase of entropy, is also tied to the nature of gravity. If this theory turns out to be true, then understanding gravity means understanding the flow of heat, the nature of energy, and the final fate of the universe itself. Exploring new scientific theories isn't just for school. It's what drives new inventions in the future. If the thermal theory of gravity turns out to be right, the cool new technologies we could make might change our world in ways we can barely imagine right now. The biggest use would be for new ways to make spaceships move that don't need to shoot out stuff like rockets do. Imagine a spaceship that could change the temperature of space around it. By making it super hot behind and super cold in front, it could, in theory, create a gravity field, like a slope in space, to push itself forward. This would be the best way to travel ever. We could travel to the stars not by pushing hard, but by gently riding a wave we create in the fabric of the universe. A thermal warp drive like this would use much less energy than any engine we have today. It could let us travel between stars in a human lifetime, opening up the galaxy for us to explore. Of course, building this would be super hard. We'd need to figure out how to make and control really big temperature differences in the emptiness of space. But knowing it's even possible would be the first huge step. Beyond just moving spaceships, being able to control gravity could completely change how we make energy. The theory links gravity directly to how heat energy moves. Could we use this process? Maybe we could build power plants that get useful energy from the natural gravity and heat differences in our own solar system. Or maybe we could make small controlled gravity fields to help with energy breakthroughs, like making nuclear fusion more steady and efficient. Controlling gravity means controlling the very fabric of reality, and the chance to use that power would be a game changer for humans, giving us clean, endless energy. In the end, trying to understand the universe is the strongest force for human progress. Even if the thermal theory of gravity turns out to be wrong, trying to prove it will teach us so much. It will make us build new kinds of experiments, make more exact observations of space, and think about the universe in new ways. It's by chasing these big, sometimes weird ideas that we find the way forward. Whether we ever build a thermal warp drive or not, the journey to find out if we can will surely make our science better, expand what we know, and bring us one step closer to our place in the universe.